10 o'clock, uh, February 25th, and it's a Tuesday. So you should have done 8C homework, linear inequalities. Hopefully that went okay. Um, if you're still stuck on them, send me a message and maybe I can help you if you're having trouble with any of those problems. But today we are gonna go over the first section of chapter 9, which will go back to matrices, and we will start studying matrix algebra. That's what we're gonna do. So we'll have 3 sections of matrix algebra, and then chapter 10 will be Markov chains. So that'll conclude this semester for us. So that's the idea. So we're gonna start on 9A today. And there's a lot of arithmetic. I don't think there's a single word problem associated with it. So it is, just compute this, right? Just a lot of arithmetic, but not a lot of word problems or anything like that. That's the schedule for the remainder of the class. Again, I have a proctoring session on Thursday, March 6th. If you cannot come to class come to class physically or come to the Zoom session on March 6th, you need to make arrangements with Smarter Proctor. I cannot make those arrangements for you, so you will have to do that yourself, and you should do that right now if that's the case. Okay. So there are some easy problems and some hard problems, but since we haven't looked at matrices in a while, we should go over all of it. So the first few problems are just identifying what's going on. They give us some matrix, which you can just think of as a table of numbers. It's just that's how the computer thinks of it. When you program these things, the computer is just thinking of it as a table of numbers, and that's what it is. Before we had it corresponding with equations, but you don't have to. It can just be thought of as a matrix and then used for other things. It's used for other things other than linear equations. Okay, but for this particular homework problem, it says determine the entries. And it says A21, A21. So it's not 21, it's 21. And that's going to be row 2, column 1. So this means row 2, column 1. Where's that? That's right there. So that is the value, the entry of row 2, column 1. Okay, so it's just -2. What is A13? That's row 3, column, sorry, row 1, column 3. Row 1, column 3 would just be this number 1. Okay, so it's just identifying where these things are located. This is A32. You can think of Battleship if you ever played Battleship as a kid. Um, you know, that's kind of like a matrix too. So 3-2 would be row 3, column 2. Row 3, column 2. Row 3, column 2 would be right there. So it's just identifying where these pieces are and how to think of them. Okay. Later, we will actually have to compute some things with our matrices. Today we're going to learn how to add, subtract, and multiply with matrices. But for the first few problems, we're just identifying where things are. It says hit. The standard convention for notation is a capital letter to represent the matrix, while a lowercase letter represents the entry in the matrix. And the double subscript shows the row and the column of that entry. For example, P12 denotes the entry row 1, column 2 of the matrix P. Okay, so that's the idea. But that's just identifying where things are. Okay. In this problem, it looks like we are going to do some addition. So I have the matrix J, I have the matrix K, and it wants to know what is J plus K. J plus K. All right, let's see if I can find that. J plus K is 2, 3, -3, -2, 1, 3, 4, -1, 4, plus 3, 1, 2, 3, 0, 4, -2, -2, 1. And the way that matrix addition happens, they have to be the exact same dimensions. The matrices have to be the exact same dimensions. This is a 3 by 3. This is a 3 by 3. So we're fine. We can add them. They have to be the same dimensions for that to happen. Okay, if they are not the same dimensions, we cannot add them. All right, so what is J plus K? You add entry for entry, entry for entry. Okay, so in this case, in the first slot, row 1, column 1, you are just going to add those two numbers together. We just add them together. Okay, well, 3 plus 2 is 5. So you're just adding them together, right? -2 plus 3 is 1. And I will say, in this lecture, I unfortunately point to the board a lot. So I don't know how that's going to translate because when I rewatch these videos, you can barely tell what I'm pointing at all. So, for instance, online folks, if I'm pointing to something and it's not clear, do not hesitate to ask me what I pointed at or anything. But I do point. It's hard for me to teach this one online because I'm pointing to things and you can't really see what I'm pointing at. But I'm just adding entry for entry. So the next thing would be 4 and -2, and that would just give me 2. So I'm just adding entry to entry. That's about as easy as it could get. Then you have 3 and 1 gives you 4. 1 and 0 gives you 1. -1, -2, -3, -3, 2 is -1. 3 and 4, 7, 4 and 1 is 5. Okay. As easy as it could be. Entry for entry. Now, it wants to know what is K plus J, and then it wants to know, is that any different? Is that any different than what we just did? Okay, so now it wants K plus J. And will that be any different? Well, we add entry to entry. So I would think it would work just like normal addition. Three and 2 gives me 5. 3 and -2 gives me 1. -2 and 4 gives me 2. 1 and 3 gives me 4, 0 and 1, 1, -2, -1, -3, 2 and -3 is -1, 4 and 3 is 7, 1 and 4 is 5. And that's the exact same thing we had last time. So it's the same. It's a true statement. So because it works entry to entry, it works like normal addition, and you can add numbers in either order and it works. So that's fine. The sad thing is it's not going to work for multiplication. The order will matter for our multiplication, but it doesn't for addition. So that's kind of nice. Like 10 years ago, I taught my niece, it's like 4 or 5, I taught her how to add multiple matrices. I think she was in kindergarten or something. And it looked like she was doing something really fancy, but really she was just adding numbers that she already knew how to do. But it looked like it was really something. Okay. So we have B and C, and then once C minus B, B minus C. I don't think these will be the same because subtraction doesn't work that way. Order matters, right? So 5 minus 3 is not equal to 3 minus 5. So I would assume order matters in this case, but we can show that that's true. All right, C minus B. C minus B, -5, 2, -2, -2, 4, 3. My B is 4, -2, 0, 3, -4, -3. Oops, and we want to subtract them. So we're going to subtract them. Okay, C minus B. All right, it works just like normal subtraction. So this would be -5 minus 4, which would be -9. -2 minus 0 stays the same. 4 minus -4 would be 4 plus 4, which is 8. And 2 minus -2 is going to be 2 plus 2, which is 4. -2 minus 3 would be -5. And 3 minus -3 would be 3 plus 3, which is 6. So it's kind of as you would expect. I mean, it's just subtracting all over again. It happens in the order you think it would. There's no real super tricky part to this. And I would assume this will be different, even though it's the same matrices, but I'm subtracting them in the opposite order. And just like standard one-dimensional numbers, order matters, so I would assume order would matter here. But again, they have to be the same dimensions for you to be able to subtract them. 4 minus -5 would be 4 plus 5, which would be 9. 0 minus -2 would be +2. -4 minus 4 would be -8. -2 minus 2 would be -4. 3 minus -2 would be 3 plus 2, which is 5. -3 minus 3 would be -6. And that's not the same thing we got last time. Seems like order matters. We're given a matrix A, a matrix B, and we want to know what is 5A plus 2B. This is called scalar multiplication. Where you are multiplying a matrix just by a number. So for instance, 5A, every entry in A will be multiplied by 5. So everybody gets multiplied by 5. And that works pretty much exactly like you think it would. Not super sophisticated. And then 2B, everybody in B is going to get multiplied by 2. Six, 10, -6, -2, 2, -10. Okay, and then they want me to add those. Okay, so 5A plus 2B equals 5, -5, -15, -15, 15, 20, plus 6, -6, -2, 2, -10. Okay. So we're just going to add entry to entry. So 5 and 6 is 11, -15 minus another 6 would be -21. 15 and 2 would give me 17. -5 and 10 would give me a +5. -15 minus 2, -17. 20 plus -10 would give me +10. Every entry is multiplied by 2. So 2B, everybody gets multiplied by 2. So you're just doubling every entry. It's not so bad. So far, not so bad. But multiplying does not work this way. We can't just multiply each entry by each entry. We have to do something different. Which also means when we square a matrix, it works differently as well. But adding and subtracting is fairly simple. You just do it to each entry. It has to be the same dimensions, otherwise it doesn't work at all. Otherwise it doesn't work at all. Online folks, does that make sense what I'm doing? It's just as easy as adding and subtracting was before, except now it's in a table of values. Okay. Here comes the first, I don't want to say difficult because it's not that bad, but here comes the first not completely trivial problem. It says determine x and y such that the following matrix is true. We have two matrices and it's adding to another matrix. So like before we have A and B, they're adding it together. Maybe this is, we could just call this A plus B, or we could call it C or whatever, but you're just adding two matrices there. So it wants me to find what are the values for X and Y, which makes this true. What are the values for X and Y which make that true? Oh, we also have an X here too. So they're adding two matrices. What would cause this to be true? Well, let's see. So for this x minus y up top, that's going to be added to that -3, and it equals -2. So taking it a little bit out of the matrix, let's look at that. -3 plus x minus y equals -2. And then this other one, everything had to do with column 2. So it says that 2 plus x equals 2x plus y. We're trying to solve for x and y now. Hey, how can we do that? Well, we have a lot of techniques how to do that now. We've done a lot of two equations, two unknowns. We've done another matrice with this. So somehow we should be able to pull this together. Okay, I might have to do a little bit of algebra and rearranging things though before I solve it. So let's see, we have -3 plus x minus y equals -2. And I could rearrange that to be x minus y equals 1. That looks good to me. I'm just moving the 3 on the other side. I get x plus 1. Maybe I should switch colors so it's clear what I'm doing. I'm going to rearrange this. I want everything, all the x's and y's on the same side. So I think I'm going to subtract x on both sides, and that would give me x plus y equals 2. So I think I have a plan now. I have x plus y equals 2. I have x minus y equals 1. I think if we just added these things up, we would be ready to go because y's are equal and opposite right now. So this would give me 2x equals 3. And that implies that x is 3 halves. And if x is 3 halves, y would be 1 half. So we have x equals 3 halves, y equals 1 half. Okay, it wanted it as decimals. So 0.5 and 1.5. Any questions, comments, concerns about that problem? So that's usually the first tricky one for chapter 9. So hopefully it's clear how I was thinking about it. And let's look at the next one. If the last one was okay, let's look at this one and see what it brings. We get matrix A, B, and C. Determine if the following operations is defined, yes or no. So with addition or subtraction, they have to be the same dimensions. So if it's 2 by 1, the only way we can add it is it has to be 2 by 1. They have to be the same. They have to be the same. For multiplication, the inner dimensions have to be the same. So for multiplication, let's say we have m by n by, I'm going to do the same thing the textbook would have done. These are the dimensions, m by n by p. The inner dimensions are same. Okay. And I'll it's not just this. This is just getting us started. We're gonna see examples of that. But if you have a 2 by 2 matrix, for instance, so for instance, if you had A is a 2 by 2 matrix, you can multiply that by any other matrix, but the inner dimensions have to be the same. So I can have 2 by 7. It just that inner dimension has to be the same, otherwise it doesn't work at all. We'll see why that is in the next problem. But right now, we're just seeing, is it possible? Okay, so here with A and B, well, what do we have? We have a 2 by 1, we have a 3 by 4, and we have a 4 by 1. So when we're adding them, they have to be the same dimensions, but these are not the same. So 2 by 1, 3 by 4, not the same. So that's, no, we can't do that. It's not defined. Not defined. In fact, none of those are the same. The 3 matrices they gave me are not the same dimensions. So I can't add any of them. There's no combination there that I could just add them. So that's not going to work. Is there a combination where we could multiply them? Again, the inner dimensions have to be the same for multiplication. Otherwise, it doesn't work. So with AB, we have 2 by 1, and B is 3 by 4. These are not the same. So my answer is no. Okay, it asks for BA. Well, that's 3 by 4, 2 by 1. Those inner dimensions are also not the same. So I'm going to put no. What about AC? That would be 2 by 1 and 4 by 1. And these inner dimensions are not the same. Not the same. What about CA? That's 4 by 1 and that's 2 by 1. And those interdimensions are not the same. So I would put no. What about BC? Three by 4, 4 by 1. The interdimensions are finally the same. These are the same interdimension, same. Okay, so this it doesn't ask what it will output, but it's going to output the outer dimensions. So it's going to give us a 3 by 1. We're going to see that in the next example. Right now, we're just identifying what's happening. CB for mine would be 4 by 1 and 3 by 4. And these are not the same. So it's no. So with multiplication, the interdimensions have to be the same. Otherwise, we can't do it. With addition or subtraction, and subtraction with matrices is really just addition again, they have to be the exact same dimensions, otherwise they're not defined. But we're going to get practice with actually multiplying them, not just discussing whether or not it theoretically makes sense. If A, B, and C are 2 by 2, 2 by 6, 6 by 9 matrices respectively, determine which of the following products are defined. For those defined, enter the size of the result matrix, ergo 3 by 4, with spaces between the numbers and X. For those undefined, enter undefined. A squared. So this is A, this is B, this is C. So A squared is 2 by 2. The inner dimensions are the same, so it will output the outer dimensions, and we get 2 by 2 again. CB. CB. 6 by 9.
What?
Hello?
10.
No one's in there either.
Ty, did you have a question? Six by 9, 2 by 6. Inner dimensions are not the same. Not the same. Undefined. AC. 2 by 2. 6 by 9. Also, inner dimensions not same. AB. 2 by 2. 2 by 6. Those are the same, so it's going to output the outer dimensions, 2 by 6. So again, this problem, we are just finding what are the dimensions. We didn't actually multiply anything. We didn't get a chance to multiply it. If they are the same inner dimensions, then it'll output the outer dimensions. But I promise we're gonna see this, not just talk about it. This one would be 1 by 1, 2, 3, 4. And this one would be 1, 2, 3, 4 by 1. So can we do this? I think so. 1 by 4, 4 by 1. The inner dimensions are the same, so it'll output a 1 by 1. So this will be the result. It's going to give me a 1 by 1. Now, we're actually asked to find what is that value. And here's maybe not the best first example, but it's our first example. And you're going to do row by column, okay? So we know we're going to end up with a 1 by 1. But how do you do it? So you're going to say -2 times 4, -8. 1 times -4. And that's going to give me a -4. So I'm going to say -4. -2 times -3, +6. 1 times -1 is -1. This will add up to one number. Okay, this will add up to one number. So this is the matrix, which is a 1 by 1. And it's just the number -7. So it's row by column. Row by column. All right. Questions about that one? Next one is going to be a little bit more involved. And this is the one where I'm wondering, I also noticed that when I look at the videos, for some reason, it's like flipping the orientation. I don't know why it does that. All right, online folks, here's how you do it. Row by column, row by column, row by column, row by column, row by column. Okay. I'll write it out as much as I can, but that's how we're going to do it. So we have a 2 by 2, a 2 by 1. So we can expect a 2 by 1 to come out. The inner dimensions are the same. It's going to output 2 by 1. That's the idea. All right, let's see that it does. 2, 3, 3, 5, 6, -9. Okay. It's going to give me a 2 by 1. So it's 2 times 6, which is 12, and then 3 times -9, which is -27. That's first row, first column. First row, first column. Next, second row, second column. Or second row, first column, I should say. 18, 3 times 6, 18. 5 times -9, -45. What does that equal? Subtract 1, that gives you 1. Subtract 2, that gives you 5. 15. 2, 25, that's 27. Okay. Negative 15, negative 27. Okay. I still don't think you really get the flavor of this until you start doing 2x2s or 3x3s, which I'm going to do this morning. So you'll get a feel for that. Yeah, so that's the idea. Are there any questions about that? This one wants me to find D times D and D times C. We will see that they are not the same. They are not the same because order matters with matrix multiplication. Let's see if I can show that rather than just saying. Okay. So this is 2 by 2. This is 2 by 2. Inner dimensions will be the same either way. We're going to get a 2 by 2 out. Either way. Either way. All right, let's see what happens with CD. CD, I'm going to write it down. -1, 4, -5, -6, 6, 1, 1, negative. It's row by column. Row by column. So row by column. So for that first row, first column entry, I'm going to multiply the first row by the first column and add it all up. Okay. So for instance, -1, this is the part where I start pointing at things. -1 times 6 is -6. And then -5 times 1 is -5. So that's first row, first column. We're going to put that together and we're going to find that that's -11. All right. Now I want to do first row, second column, because that's the entry I'm finding. So that's -1 times 1, which is -1. And then -5 times -3 would be +15. And we're going to add that together and we'll find our 14. But I can do that in another step. Okay. Now, this entry here that I'm finding is second row, first column. Second row, first column. So that's 4 times 6. And that's -6 times 1. And we'll find that's 18. And then last, we want second row, second column. So that's 4 times 1. And that's 6 times, -6 times -3 would be positive 18. Okay. Any questions about where I got any of those numbers or how I did that? Okay, well, lucky for you, we're gonna do it again. We're gonna do it in the other order. And we'll find it's not the same. We will find it's not the same. So let's find D, C, and see what happens. So that would be 6, 1, 1, -3, -1, 4, -5, -6. Okay, let me make sure I wrote this down right. 6, 1, 1, -3, yeah. -1, -5, 4, -6. Okay. Now, same old thing. Okay. Row by column. Row by column. That will give me -6. And then 1 times 4 will be +4. So that'll give us -2. Row by column. So that looks like it'd be -30. And then this would be -6. So we'll find that to be -36. Row by column. 1 times -1. -3 times 4 is 12. So we'll find that to be -13. Row by column. So that would be -5 plus 18. We'll find that to be +13. Not the same. It is not the same. So multiplying in 2 dimensions is not the same as multiplying in 1 dimension. So order matters. They are not the same. CD is not the same as DC. Order matters. There are some matrices where order doesn't matter, but in general, it does. In general, it does. There are some matrices where order doesn't matter. You can multiply them either way, but in general, it does. So in general, it does matter. Any questions about that? Evaluate the matrix product. This is a 3 by 2, 2 by 2. So this is going to output a 3 by 2. 3 by 2, 2 by 2. These are the same inner product, or it's the same inner dimensions, so it will output the outer dimensions. And that's what the computer is sitting there waiting for. It's for you to put in those values for the outer dimensions. Okay, so let's find what those are. -1, 2, -3, 2, 2, 3, and -4, -3, 5, 3. So we're going to get a 3 by 2 out of this process. Row by column. Row by column. Let's see if we can find it. Row by column. So -1 times -4 is 4. And then 2 times 5 is 10. Row by column. And this is first row, second column. So we multiply first row by second column. So that's 3. and then plus 6. And now we want second row, first column, so we'll multiply second row, first column. So this will be 2 times -4 is -8, and 2 times 5 is 10. Find that to be +2. Now we want second row, second column. Okay. So that would be -6, and this would be +6, and we'll find that to be 0. Now we want third row, first column, third row, first column. -3 times -4 is +12. And then that would be plus 15. So we'll find that to be 27. And then third row, second column. -3 times -3, +9. 3 times 3, 9. Is it clear how I did that? Are there any questions? I'm trying to map this out. So if you look back at it, you can see where it came from. But I don't know how good I'm doing. Hopefully it's clear where these numbers are coming from, how I'm multiplying them. And order does matter. So if I multiply these matrices in the other order, it's not the same. In fact, it's not even possible. Please stop me if you have any questions about this. All right. So it wants A times 2B. 2B. How do you find 2B? Multiply every entry by 2. So I'm multiplying every entry by 2. Now, what's A times 2B? A 2B would equal -7, 4. Need like a TV producer to come in here. -10, -4, -2, -2, 16, 18. Okay. So let's try to multiply that. This is a 2 by 2. This is a 2 by 2. So we should get back a 2 by 2. So row by column. Row by column. So -7 times -2 would give me +14. -10 times +16 would be -160. row by column. So you get 14 again, and then negative 180. Row by column, negative 8, negative 64. Row by column, negative 8, negative Hopefully, it's clear how I'm doing the matrix multiplication. Really trying to color code it, so when you come back to it, be easy, but it's also one of those things that just takes practice. Okay, so you're doing row by column, and then once you get those, put those values together. Okay, I don't wanna say adding, cause sometimes, like technically, am I subtracting or adding that kind of thing, but you're putting them together, right? This one's a cubed. A cubed. What's a cubed? That's a times a times a. That's a times a times a. Now, I'm not going to do that. What I'm gonna do is I'm gonna find a squared and multiply that by a. I'm not gonna do it 3 times. That's not how I do it. So the way I'm gonna do it is I'm gonna find a squared first, and then I'll multiply that by another a, and that will give me a cubed. Okay, so my first hope is, can I find a squared? Well, we've had some practice with matrix multiplication, but as we know, it's easy to make a mistake, and if you make one mistake, the whole thing falls apart. Okay, so row by column. If you see me make an arithmetic mistake, please call it out. All right, negative 3 times negative 3, 9. 1 times 0, 0. Oh, that wasn't so bad. Row by column. Negative 3 times 1 is negative 3. And then that would be another minus 1. Okay. Row by column. 0, 0. That wasn't so bad. And row by column. 0 times 1. Or plus 1. Okay, so I think that's it. I think that's a squared. Hopefully I didn't make a mistake. 9, 0, negative 4, 1. That's a squared. It's not what the question asks, but it's what I'm going to use. When we used to do the IU test, you'd have to find like a to the 16th. And the next step, what you would do is you do a squared times a squared, a to the 4th. and then a to the fourth times a to the fourth, a to 8, and you just keep going that way. But we want a cubed. So if we want a cubed, I think we can do a squared times a, and that'll get us where we want to be. So my new matrix times the original should give me a cubed. So I think that's 9, -4, 0, 1, -3, 1, 0, -1. Okay. So once again, row by column. Row by column. If you see me make an arithmetic mistake, please call me out. -27 plus 0. Row by column. 9 plus 4 should give me 13. Okay. Row by column. 0 plus 0 is 0. Row by column. 0 minus 1. So there it is. Is there any questions about how I did that? Questions, comments, concerns about how I found a cubed? So if I wanted to find a to the fourth, I could either do a squared times a squared, or I could do a cubed times the original. That's my choice. And now I could just build up from there. If I wanted to find a to the ninth, I might just keep going with my a cubes. If I wanted to go a to the 12th, I might keep going with this. But you can build up that way. You can build up going this way. And that way you're not doing 3 or 4 in a row. You're only dealing with 2 matrices at the same time. So that's also important. Any questions about how I did that? Okay. Perform the following operations. We want to multiply these matrices. Note, the entries in the resulting matrix are functions of A. Okay, good to know. So what will this give me? Is there enough room? Manipulate Zoom's PDF, not Zoom, Chrome's PDF. Maybe. Row by column. Row by column. And what do we have here? We have a 2 by 2, and we have a 2 by 3. So we're going to get a 2 by 3 out of this. Okay. So in that case, I'm going to get a times 1, which is a, and then -1 times 1 minus a. And that's too complicated for me to think about in my head and solve it. So I'm going to go -1 minus a, and I'll leave that for another step. Okay, next it's row by column. So that would give me 3a plus 4 times 1 minus A. Row by column. That's negative 5A plus 3 times 1 minus A. Row by column. And that's going to be 1 plus A plus A. Row by column. Row by column. 3, 1 plus A minus 4A. Row by column. 1 plus A times negative 5 minus 3A. Oops. Is that step okay? Is it clear how I'm multiplying them? So the remaining step is to simplify that. I just need to simplify it. So that's minus minus A, so that's 2A minus 1. And that's 3A minus 4A. So that would be 4 minus A. And that's negative 5A minus 3A, that's 8A plus 3, that's 3 minus 8A. 1 plus 2A. 3A minus 4A is minus A. 3 minus A. Negative 5A minus 3A would be negative 8A. And that's minus 5. Okay, that's what I think the answer is. Is there any questions about that one? Let's see if I fix. This one's the identity matrix. The identity matrix is either just number 1. If it's 2 by 2, it would be it always has a diagonal of 1s. Everything else is zeros. It acts just like the number 1 does in our normal one-dimensional numbers. Okay. So in this case, it wants me to multiply the A by the identity matrix. What does that equal? Well, I claim that's going to work the exact same way as multiplying by the number 1. So the identity matrix is a square matrix where the diagonal is 1s, everything else is simply zeros. It acts just like the number 1 does in our normal arithmetic, and I think it will act the same way. So again, notice what will happen. So you have 2 times 1, you just get 2, and you get -1 times 0, and -2 times 0, and those just drop off. And then for your first row, second column, notice what will happen here. So you'll get 0, and whatever the entry was there, then -2 times 0 is 0. So you only get that middle entry in that time. Here, first row, third column, 0, 0, -2. Similar, second row, first column, I'm going to get whatever I had, and everything else will go to zeros. Second row, second column, 0, -4, 0. So that's done. Second row, third column, 0, 0, 4. Third row, first column, just get -1. Third row, second column, 0, 0, 0. Zero, zero, zero. Did I get the exact same thing back that I put in? Yes, and that will always happen. Okay? So A times the identity matrix is A. Always. It's always true. You'll always just get it back. And we'll need that tomorrow when we study division. So we'll need the number 1 to be able to do this. I claim it will happen the exact same way going the other way. Even though matrix multiplication is non-commutative, it will still work. The identity matrix acts just like the number 1. I times A equals A. It'll be the same thing. It'll just be A again. Whatever your A is, it'll just be A again. So with this, it acts like the number 1. 5 times 1 is 5. 1 times 5 is 5. So order doesn't matter with the number 1. All right. This one, pretty similar. We're just going to multiply them, see what happens. Are they the same in either order? I'll just tell you, no. Order matters with this. They are not of the same order. So when we multiply them, we should get something else. We will get something else. Not should. We will get something else. Okay? And then I think here's the last one. You get A. They want A squared. A squared, you just multiply it against itself. We already saw one where I did A cubed. So those last two problems are very similar to ones I already did. So hopefully hopefully that can at least get you started. And if you run into trouble, you can send me an email or message through Ivy Learn, and I'll respond as quickly as I can. All right, it's technically my time. I'll stick around for what questions there are. Your homework should be open now or within 1 minute, but I'll stick around for what questions there are. Tomorrow we'll learn about how do you divide with a matrix. We did add, addition, subtraction, multiplication today. Tomorrow, what is division like with matrices? And then 9C we'll be able to do some algebra. All right, I'll stick around for what questions are. Otherwise, I'll see you tomorrow.